Welcome, my dear students. The second method of numerical solutions of equations is Newton-Raphson method. So already in the previous video, you have seen that how to find the rough location of the root. Number two, how to improve the root by method of tabulation and method of bisection. And bisection method is a very important method because it surely converges the root. In this method, you will get surely a root, and it is a iterative method. And because of the NIP property, now in this lecture, we'll talk about Newton-Raphson method. That is also a very beautiful method. You will see. In this method also, we assume that the function fx of the equation fx equal to 0 is continuously differentiable sufficient number of times. Also, we assume that all the roots of the equation fx equal to 0 are simple. First, we find by the method of tabulation a sufficiently small interval a naught b naught containing the only root alpha of the equation fx equal to 0 such that f a naught f b naught less than 0. So you need a rough location of the root first. So your initial approximation must be very close to the root. Otherwise, in this method, the root will diverge. That is a very important concept actually. Be careful about that. The iteration is generated by the formula this. This is the generated iteration is generated by this formula. Xn plus 1 equal to xn minus fxn by f dash xn, f prime, that is the derivative. And we'll prove this iteration formula. How to get this iteration formula? Starting with x naught equal to a naught or b naught. So this is your initial starting point, initial guess, we must say. So this is the iteration steps. Xn plus 1 equal to xn minus fxn by f dash xn. The iteration is a particular case of the fixed point iteration. We'll see my next videos on fixed point iteration also, in which fx is equal to 0 has been written in the form x equal to phi x equal to x minus fx by f dash x. So that phi dash x, if you differentiate phi prime, then it is given by fx minus f double prime by f dash prime square. And you know that for the condition of convergence is modulus of phi dash x less than 1 for any iterative method. That is the condition of convergence for fixed point iteration. Condition of convergence. Modulus of phi dash x less than 1. So therefore, in this case also, you are getting a condition of convergence for Newton-Raphson method. This is the condition of convergence. Condition of convergence, not order of convergence. And the most important thing in Newton interpretation is geometrical interpretation in Newton-Raphson method. Actually, this gives us the idea what is doing in Newton-Raphson method, what we are doing actually in Newton-Raphson method. The geometrically, Newton-Raphson iteration is that the point at which the tangent to the curve at the point xn fxn cut the x-axis is xn plus 1. For the tangent at equation y minus fxn equal to f prime xn x to x minus xn. And this tangent cut the x-axis at, that is y equal to 0 at x equal to xn minus fxn by f dash xn, which is nothing but your second approximation or n plus 1th approximation, xn plus 1. That is why Newton-Raphson method is also known as the method of tangents. Let us observe it is geometrically, graphically. So this is your curve fx curve, and this is your xn point, and this point is fxn. So this is the point in a two-dimensional axis, and this is the root alpha. So this point is actually xn comma fxn. Okay. And the tangent at xn comma fxn is given by, what is the tangent? The tangent is y minus fxn equation of the tangent equal to a prime xn times x minus xn. This is the equation of the tangent. Okay. And at which point it cuts the x-axis? How we look at? Substitute y equal to 0. So y equal to 0 gives you the point x equal to xn plus minus fxn by f prime xn. So this is gives you the xn plus 1. Next, at xn plus 1, again draw a tangent. Again draw a tangent. Look at that. This tangent will intersect at xn plus 2. You got a second approximation. And so on. And look at that. Very fast the approximation tends to alpha. That is very fast the method converges to alpha. So that is why this method is called method of tangents. This is the diagram, this is the geometrical interpretation of the Newton-Raphson method. And why the method is called method of tangents. Look at another method, how the point converges to exact root. So your exact root is this, and this is how your root converges. This is the first approximation x1, next approximation x2, next approximation x3, and the next approximation x4. This is how the method converges very fast. So this is very fast converges. That means, but look at that, your initial guess is very, very important. If your initial guess is far away from the root, then it is very, very difficult to converge the root. It will diverge in that case. It will diverge. And so, and look at that, it is very fast convergent. That means the order of convergence must be more than 1. We will see what is the order of convergence of the method. We will check the order of convergence of the method also. So I will show you one diagram where if the initial guess is not close to the root, it will diverge. So if you see the approximation is somewhere in the curve away from the root, it may not converge. Okay. Now let us have alternative derivation of the method. Let xk be an approximation to the root of the equation fx is equal to 0. And let delta x be an increment in x such that xk plus delta x is an exact root. Therefore, f of xk plus delta x equivalent to 0. Now apply Taylor series approximation, expanding with respect to Taylor series. You will get fxk delta x f dash f prime xk 1 by factorial 2 delta x square f double prime xk etc. equal to 0. Neglecting the second and higher powers of delta x, because delta x is very small, so you are neglecting the higher powers of delta x. We obtain fxk plus delta x f prime xk approximately to 0. So delta x is approximately minus fxk by f prime xk. Okay, this is your delta x. So your xk is xk plus delta x actually. So hence we obtain the iteration method. Xk plus 1 is equal to xk plus delta x, and delta x is nothing but you look at that minus fx by fxk by f prime xk. So you have the iteration formula. Okay, this is the method of finding the iteration formula, and you can find it by geometrical method also. I that already explained to you, by method of tangents also. Now let us calculate the order of rate of convergence or order of convergence of the method. Let xi be a root of the equation f x equal to 0. Then f xi equal to 0. Now the iteration scheme for Newton-Raphson method is xn plus 1 equal to xn minus fxn by f dash xn. Right? Let xn equal to epsilon n plus xi. Therefore, above relation becomes, if you substitute epsilon n plus xi equal to xn is nothing but your epsilon plus xi. You know that uh, xn is epsilon plus xi and xn plus 1 is epsilon n plus 1 plus xi. This should be, yeah, this should be epsilon n, sorry. And if xn is f of epsilon n plus xi, f prime xn is f prime epsilon n plus xi. Cancel xi from both sides. You have epsilon n plus 1 equal to epsilon. Then apply Taylor series expansion. If xi plus epsilon n, if prime xi, etc. And denominator also, you are applying Taylor series expansion on f prime, neglecting the higher order terms. And with the fact that f xi is 0, because xi is a root, so you have this simplified form. And expanding in binomial, negative binomial expansion, this term can be, so this term can be calculated. So look at that, expanding in negative binomial. And finally, if you do the calculation, you will have an higher order term epsilon n cube is neglected, and you have epsilon n square minus epsilon n square by 2 f double prime xi by f dash xi plus epsilon n square f double dash xi by f dash xi. And finally, you have epsilon n square by 2 f double dash xi by f dash xi. Now, this is nothing but you can write epsilon n plus 1 by epsilon n square equal to a. That is epsilon n plus 1 by epsilon n squared modulus of this is equal to a. A is nothing but your f double prime xi by f dash xi. So this is your limit. This a is your asymptotic error constant and p is your 2. Already we explained in the previous video, order of convergence of the method. 2 is the order of convergence. P is actually the order of convergence of the method. So Newton-Raphson method has quadratic convergence or second order convergence. That is why the method is rapidly convergent, very fast. In few steps, you will get the root, approximate value of the root in very few steps. And you can easily write the programming language for this also. This is very easy. So this is how you can calculate the order of convergence of the method, Newton-Raphson method. Okay. Next, we'll talk about some applications. We can find out the kth root of a number. So if you're a kth root of m, x, you write x equal to m, kth root of m, x to the power k minus m equal to 0, you write fx equal to x to the power k minus m. Now iteration scheme is found by this substitute in the Newton-Raphson method iteration scheme. You substitute, you will get the iteration scheme here for the kth root of a number. This is the kth root of a number. Also, you can calculate the multiple root by Newton-Raphson method. It's generalized. You have to use a generalized form. So Newton-Raphson method generalized form is given by xn plus 1 equal to xn minus p fxn by f prime xn. Gives a faster convergence sequence. Okay. And for complex roots also, Newton-Raphson method can be used to find the approximations to the complex root. That I am not explaining in this lecture. So this is the very beautiful video for Newton-Raphson method. So I will solve some problems very soon and I will give you some assignments on these methods. So in the next lecture, I will talk about fixed point iteration, and subsequent videos I will talk about regular falsy method also in next week. Thank you all of you.